All right, everyone. Thank you for coming. I'm Cherie, and with me here is Mohammed, and we're going to talk a bit about how to think about and how to ensure safety in the real world. So we have three key purposes of this session that we hope to achieve. First, by outlining some key challenges in current methods, both in the engineering paradigm and in the formal paradigm, how to guarantee safety. Second, we would like to build some intuition behind two key formal safety proofs and where these guarantees can be violated. And third, to give us all some hands-on experience and getting our hands dirty with guaranteed safe control. And we will also play with one canonical use case on where this can fail, and we'll try to fix it. All right. So in order to achieve that, first, we'll kind of go through the context, challenges, then we'll talk about the math formulation needed for these safety proofs and two formal tools. We'll also comment on how these kind of relate into the real world, then we'll end with our interactive session. So kind of leaping from what Basti talked about last time, we now have nominal algorithm that works relatively well in a lot of wilderness applications. However, robots are still kind of limited to these specialized wilderness due to the heavy hand tuning and engineering needed for a particular mission. In addition, there's also a lot of potential out of normal cases that our nominal algorithms may not be able to handle, and therefore we still require one or multiple safety pilots at the ready to take over. And in a way to address these kind of out of norm cases, we also have handcrafted safety mechanisms in order to enable safety. However, these are for very specialized cases. So how do we get from here to kind of our vision of ubiquitous autonomy? What we mean here is we envision a world where autonomy is seamlessly integrated into our lives at scale. And in order to allow for that, we first need to kind of address the generalizability of our algorithms and rely less on the hand tuning that is needed, be able to handle out of norm cases and be self-accountable. So being able to handle these out of norm cases without necessitating the safety pilots. So kind of graphically, kind of looking at the timeline and the level of risk, currently we're at, beforehand we were at very controlled environments, indoor environments, cage, where we're able to begin our kind of like robotics algorithms. And now where we're at, we have a lot of success in kind of bringing out these cage algorithms into the wild. However, requires a lot of hand tuning and handcrafted safety mechanisms in order to enable safety for those specialized cages. Looking forward, we hope to go towards ubiquitous autonomy, where there's a lot higher risk due to the large number of cases that the system might be able to interact with. And so really kind of to bridge this gap to solve, again, is the generalizability issue, handling out of norm cases while being self-accountable. So to encapsulate, our key question that we defined is how can we ensure safety or guarantee safety for scalable deployment in the real world? What we mean by ensure safety is almost like ensuring there's a lower bound on risk being like the likelihood of a very bad, unrecoverable event, and kind of bounding that in order for us to be able to have scalable autonomy.
So now we're going to talk about the challenges that ensuring safety have in current methods. So we're going to look at a familiar running example that Basti introduced in his slides, which is the autonomous helicopter example. Here, we're going to add different agents, which are our dynamic obstacles. And the helicopter has nonlinear dynamics, and it can experience different disturbances, like, for example, wind disturbance. And the goal here is to reach the goal point safely and without any collision. Going back to the question of how can we best ensure safety and why it is difficult, the underlying challenge is how can we balance safety and performance? And safety and performance are kind of on the opposite sides here. As you can see on the graph, we want to ensure the highest possible safety. We're going to have lowest possible efficiency, which is our helicopter should basically stay at home. That is the highest safety that it can have. And if we don't care about safety at all, it's basically at high-level planners side, which we have high-level planners which are really efficient, but we don't incorporate any safety layer into our system. But our ideal case is basically to have as much safety as we can with as much efficiency as we can. So the ideal point on right-hand corner. So the challenge too that we might have is that autonomous systems can experience many tail end cases. For example, we can have actuator failure. Here it's shown for fixed wing. In autonomous cars, we can have autonomous cars seeing itself on the back of a truck. And these are really low occurrence cases, but in real world, these cases have high impact. And we want to incorporate these cases for safety reasons, of course, but we don't want to overfit to our specific problem. So here we can have two kinds of approach. One is more generic approach, which our approach incorporates lots of different systems, but not those tail end specific cases. Another approach would be overfitting to a specific case, which has a higher safety, but possibly lower efficiency. So this challenge also falls back a little bit into safety versus efficiency. The third challenge that we can have is that nowadays autonomous systems are getting more and more complex and in a non-deterministic world. For example, these autonomous systems are consisting of a lot of different pipelines, and the pipelines themselves are getting more and more complex. For example, we are seeing rising of a lot of different and complex neural network sensing pipelines. We're having a lot of different planning algorithms, including learning-based planning algorithms. We have a lot of hand-tuned safety pipelines for specific tail-end cases. The whole pipeline as a whole would be really complex, and it's unclear how we can guarantee safety for such a complex system as a whole. Specifically, for example, for learning-based systems that we don't specifically trust them to be always safe. As a quick summary, in the graph, you can see that, as we said before, safety and efficiency are at odds with each other. And if you want a safe system, we're going to have a really conservative system, which inevitably leads to low efficiency. And if we want an optimal system with high efficiency, we're going to need a long time horizon. We're going to look at the long time horizon for planning, which might ignore safety properties. So how can we answer the question of ensuring safety? One approach is to use safety pilots in such a system, which was mentioned in Bassie's slide again. monitor system always checking for safety. And if anything goes wrong, the monitoring system pass along a warning to the safety pilot. And from then, safety pilot is responsible to take care of that situation. In such a method, the risk is basically lower bounded by the pilot's ability to handle the situation. And this system is hard to scale because we need one safety pilot for every autonomous system, and each safety pilot needs to have a lot of expertise and training, and that would be really expensive to scale. So another method would be coming up with basically a laundry list of expected out of norm cases and handcraft a bunch of backup behaviors to deal with each specific case. For example, in our helicopter example, when the helicopter is near ground, we can make the safety radius larger to account for the fact that there might be a lot of trees or buildings to crash into. Or when the helicopter is approaching a sharp turn, we can slow down to ensure safety more. So this method, because it's handcrafted, it can go needlessly complex really fast. And we can't possibly find all the corner cases and account for them. So we can't really guarantee the system is always safe. And because of that, this method also has scalability issues. So these were more engineering schemes to come to some hand-tuned system or a human system to take care of the safety issues. But today we're going to focus on more formal guarantees based on some mathematical framework and abstraction of system dynamics that can make claims or safety properties. The good thing about such methods is that these are mathematically provable and generalizable as a result. But the problem with these methods is that it always lies back into our initial assumptions. And if those assumptions are being violated, these methods are having difficulty to act, basically.
So just now, Mohammed talked lastly about the formal tools that we can, formal tools being one of the methods to ensure safety. We'll briefly talk about kind of the math formulation that is needed to provide these guarantees. Then two key tools that we use in order to verify an action, one being reachability analysis and another being control bearer functions. So to kind of start it off, we want to verify a given action is actually able to stay safe after given our key ingredients. So there are 4 key ingredients for verifying a safe action. First, we have to define a safety definition, which will be the condition where we check whether or not something is safe or not. Some examples can be staying in free space. In the autonomous driving case, it can be stay within the given lanes. And then an action, and then kind of the baby ingredients we define as the system dynamics, which defines how the system will evolve over time. And the examples of these include we need to start with an initial state. This can be an uncertain or given initial state. Then we need to define their quad rotor dynamics, the quad rotor controller. And if we deal with the multi-agent case, like in the autonomous driving case, the pedestrian modeling. The third ingredient is system limits. We need to define what our actuator limits are and sensor ranges. There are also different ones, but these are the 2 key ones. And finally, we have disturbances or noise. And some examples of these can be wind and sensor noise. So given an action can be a control input to the system or a trajectory to follow. If all cases are safe based on this definition, all cases being the bottom 3 blocks, then this action is verified as being safe. So to be more concrete about that, we go back into our running example. For example, an action can be a control input, or for now, we'll talk about a trajectory. We first define a safety definition. So a vehicle will stay within free space. We define the system dynamics, which includes the dynamics in the controller, and for multi-agent case, maybe our knowledge of the other dynamics. And then we also have system limits, which goes under the controller on what the constraints are. And then finally, we have a disturbance, and this is often in form of unbounded disturbances. I'll just wait right now if there's any questions about from this slide and the slides before. Okay, so kind of continuing on, we'll introduce 2 key tools, one being reachable set and the second being control variable functions. So the key idea of a reachable set is, for here, we focus on verifying that a trajectory will be safe. We'll be computing the set of all possible states when following the trajectory. We verify that an action or the trajectory is safe by sensing that the obstacles are outside of this reachable set. So mathematically, we can formulate this as a reachable set for a given time interval that it takes to follow a trajectory. And then this is a union of all the time and a union of all the reachable set at the different times while following. And then specifically, in the colored section, we can see how it's actually defined, where we look at all possible states of given a model dynamics following our given possible initial states, the input, which comes from the controller and its constraints, and then the disturbance. From here, you can see how our assumptions on the model, the initial states, the input space, and the disturbance is vital to a safety guarantee. So why can't we just naively kind of for loop through these? And the key challenge there is the high dimensionality of the system, and it will take a really long time in order to compute. And for our application, we're focused on real-time systems. And so we'll talk about and so one key tool to calculate these will be CORA, which is Continuous Reachability Analysis. And this is developed by Matthias Althoff, who was also here with John Dolan's lab as a postdoc. So the key idea is we have a helicopter that has a nonlinear dynamic. The key idea is to first find the reachable set given a linear dynamics, and then over approximate given the possible linearization errors. So kind of mathematically how the model has changed. First, and to the left bottom here, we have x dot f x u d. That is a nonlinear dynamics. That can be a nonlinear dynamics. We kind of switch this to, they kind of concatenate the controller and the vehicle dynamics into one, which is described by A, and then plus the disturbances and the noise as a separate dt. So kind of building an intuition on why we should start with an LTI system. Here again, we have our model AX plus dt. The key property that we leverage is superposition, which allows us to separate the homogeneous and the inhomogeneous solution. What this means is the homogeneous is the solution. So the solution being where this robot can be at time R or time T can be can be separated from where the robot can be at given the disturbances. And because these are not intertwined, that makes the computation more efficient. It's also helpful that LTI systems is a very popular system that we analyze across different engineering and physics disciplines. And so there are many well-known solutions we can use in order to aid in our solution finding. So an overview of how we can calculate these reachable sets. First, I'll talk about how to calculate it for a linear system. Then we'll talk about the modifications needed to analyze a nonlinear system for our helicopter. All right. So first, we are given a R0, which is the initial set that the system can be at. Then we calculate at the end of that time interval what the state would be at. And RHR is calculated via the third equation. I can't see my cursor, but then the third equation at the bottom, the first term. So SHA exponents AR. So we calculate it via that. Then we obtain the convex hull between the reachable state at the end and at the start. However, just doing this convex hull is only a reachable set if the robot travels straight and has no uncertainties. Uncertainties being disturbances or sensor noises. So in order to find the final interval, reachable set for the interval, we enlarge the reachable set to account for the curved trajectory and the uncertain inputs. So extending to nonlinear systems, once again, the key idea is to linearize the nonlinear dynamics, then over-approximate by the linearization error. So we do this in order to enable efficient computation. Then we over-approximate by a bound that we can derive from the differential equation of the linearization error. And then finally, for a highly nonlinear system, the linearization error can be extremely large. So we attempt to constrain it by defining a hand-tuned heuristic which is the maximum allowed linearization error, such that if a set with linearization error bounds is larger than that, we actually split the reachable set and redo that calculation to be more accurate. Of course, this is a balance between how accurate we want to be and also the compute time, as these loops would take multiples of time. So in algorithm format, I have outlined in red the key modifications we made in order to analyze a nonlinear system. And then first we need to linearize, then we need to get the set of linearization errors. And then also L bar is the hand-tuned heuristics that we talked about. So an animation of this, we have first we linearize the system, compute the reachable set by the convex hull and then the first enlargement. Then here we apply what adding the maximum allowable error would look like. Then we calculate what the actual linearization would look like. And if it is smaller than the maximum allowed, then we go ahead and use the one in red as our computed reachable set. However, in the very nonlinear cases where there's too much linearization error, we will, in order to be more accurate, we split the reachable set. So a note is in Althoff's paper where he applied this technique into the autonomous driving case, he actually, if a trajectory is outside of the linearization error, a maximum linearization error, he chooses to cast this trajectory as unsafe, as doing the splitting can lead to non-deterministic computation time, which is detrimental for our real-time constraints. So applying these concepts to our example, first let's assume the helicopter is somehow static. We try verifying one of the trajectories, and then we see from the reachable set that we can quickly calculate that it is in collision, so we don't use that, so that's not verified. And then we find another verified trajectory. So in the dynamic agent case, we can also, if we have knowledge of the action that the other helicopter can take, we can also similarly calculate its reachable set. An extension of this work also by Matthias Althoff is on stochastic reachability analysis, which he also applied to the autonomous driving case, which may make more sense as it is highly uncertain where other agents may go. So he has done some work on how to analyze these, how to account for the stochasticity. So one interesting paper work that's out of this lab is how to use this technique also to verify beyond the planning horizon. So what we talked about just now is we have one action, one trajectory, and then we verify up to that, the end of the trajectory time. An interesting insight that this paper does is we also pre-compute these. We also see if our intended trajectory, our reference trajectory, can safely enter a larger circle. And a larger circle is, you can imagine the helicopter kind of just goes in circles. This allows technically indefinite safety because that they can stay safe indefinitely. And this larger circle's reachable set is computed offline, so that online we just need to check if the intended trajectory is actually the final, can actually safely enter the emergency larger circle. So kind of like going back to our four key ingredients, here in this paper, they actually use staying in known free space. And that's because one of the limits that they talk about is actually the sensor range, where the known free space is the volume that is the concatenation of multiple kind of time steps of observations. And so that's an interesting application of the safety definition. So the result is their approach is verified using Monte Carlo simulations at different initial sets. We can see here at the top left that all the trajectories stay within the calculated reachable set, and it's able to safely enter the larger circle. So we talked about reachability analysis, and one key way that we can calculate this by over-approximating the linear dynamics. This approach scales well with the number of state dimension. However, it does not work well in highly nonlinear cases, as the linearization error might be too big, causing a lot of splitting. Yeah, so is there any questions on the set of slides on reachability analysis, the mathematical formulation, before we go to Mohammed?
Cherie?
Yep.
From the example that a reachable, area, this is like the red zone. If it is in collision with obstacles, so we consider it unsafe. Is that right?
Yes. So yeah. So if that the computed reachable set, this is how we finally verify it. It collides with an occupied state, here being the other helicopter, then yes, it is deemed unsafe.
Okay, thanks.
Bart?
Okay, so the next method that we want to talk about is control barrier function. So the control barrier functions are kind of on the opposite side of reachable sets, in the sense that reachable sets estimate the future states and tries to remove unsafe set of actions. But the control barrier function predefines the safe set and imposes the corresponding safety constraints to ensure we are safe. So basically, reachable sets take down a top-down approach, while the control barrier function takes a bottom-up approach. So as we talked about, control barrier function tries to predefine a safe set. And here we go a little bit deep into how it's actually done mathematically. Here we assume control affine form, but in terms of dynamic itself, in general form of control barrier function, we don't really assume anything. So we can plug any nonlinear and complex dynamics here and still go through the same definition of safe set. For the safe set itself, safe set is the set C, which incorporates a set of all safe states. And the way that we define safe set is that we first define the function h, which maps from n-dimensional state space into one value, which basically compresses the notion of safety in the way that we define that whenever h is positive, we are in the safe set. So h being positive means that we are safe. So to show that visually, in the example of in the simple example of two-dimensional state space, we can plot all the h values for two-dimensional state space, and we can see the plot on the left. And as you can see, the blue plane is basically our two-dimensional state space at h equals to 0. So anything above this plane would construct our safe set, which is shown as the red bowl-shaped surface. So what it means to be safe is basically for our system to keep being inside that bowl and doesn't go outside that bowl. Now that we have the notion of our safe set, how can we check for safety? For example, if we want to take an action, how can we check that that action is actually safe? You can assume that if we don't have any controller input, which means u equals to 0, we are confined on the surface of the safe set. So you can assume that we are on some point on the surface, and we want to take some action, and we want to ensure that that action is safe. One thing that we can do is that we can say we require our derivative of h to be greater than or equal to 0, which means that we can only go more inside into the bowl or stay at the same level of h, which basically ensures our safety. That is the notion of Nagumo theorem, which says the derivative of h should be always greater than or equal to 0 on the surface of safe set if we don't have any control input. So to make it more general, as an extension, we have control barrier function, which allows our control input to be non-zero. And having non-zero control input means that we are not confined on the surface of our safe set anymore. And now we can go inside the volume, which means for whichever point on the surface, we can have different control inputs, which means that we can go inside the volume now. If we have a control input, Nagumo theorem extends to this equation here, which basically says the same thing. It says the derivative of our h should be greater than or equal to 0 for all the points inside the volume of our safe set. One problem with this notion of control barrier function is that it's too conservative, which means that looking back to this point that we are in right now, if we want to abide by this constraint, the only area that is left for us to stay in is this top area. And we are losing this whole part, which is still perfectly safe, but we are not using it. So this notion of control barrier function is too conservative. As a solution to being too conservative, we can allow our derivative to go negative. But we should be careful with that, because if our derivative goes negative, if our derivative goes too negative, we can go outside the bowl and we are no longer safe. So one way we can do it is through this equation 1 here, which basically allows our derivative to go negative. So for any positive h, so for any point in the safe set, we have this constant to this positive, and there's a negative here. So we are allowing our derivative to go negative. But when we go close to that blue surface, which is h equal to 0, this whole right-hand part goes to 0, and it doesn't allow, it basically falls back to our previous notion of safety, and it doesn't allow our point to go outside the safe set. So with this notion of safety, we can guarantee that we are always inside the safe set, and we can use the whole volume, but we can never go outside. So now that we have a mathematical framework to define safety, what can we do with that? So what we can do with that mathematical framework of safety is that we can define a safety filter which lies between the controller and our system. And it basically filters the output of the controller. So controller comes up with a desired control input, and this safety filter forms an optimization problem, which you can see here, that optimizes our control input to abide by the safety restrictions, but be the closest control input that can be to our desired control input. So if our U desired is already in the safe set, this optimization problem just outputs the U desired itself. But if U desired is not in the safe set, it'll change it, and it outputs the closest U to U desired that is still in the safe set. So this whole safety filter is computationally efficient because there's some, the cool thing about it is that our constraint is in affine form, and our objective is quadratic, which forms a quadratic program which can be efficiently solved through so many QP solvers that are out there. And another good thing about it is that it is minimally invasive, which means that it only kicks in when the controller is outputting unsafe control input. Other than that, it just passes the same thing through. Now that we have our optimization problem, we will talk about a specific example of how that safe set is being constructed, basically. So here we assume double integrator for our dynamics. And for defining our safe set, we basically need our velocity-based distance between two robots to be greater than a safety distance. More specifically, we want their distance plus the distance that they would travel in a certain time to be greater than a safety distance. This notion of safety gives us the function h, which you can see here. And from the safety constraints that we found before on equation 1 and the function h that we just found, we can construct our optimization problem, which will be something like what is shown in the lower right corner. And this optimization problem is basically our safety filter, which filters our controller. To go back to our running example, you can see that here the controller for the helicopter outputs desired control input that is in collision course, and our safety filter kicks in here and outputs U star, which is closest to U desired, but still in the safe set. So the best way to show the result of control barrier function is through aggressive multi-robot application. And you can see here that the 4 robots in the middle are trying to, their controller is trying to either hold a position in hovering mode or go in a circular motion, which you will see later. And the other robot is trying to go through them, basically. And once they are in collision course, control barrier function kicks in and changes the control input for the robots to stay safe. So kind of the main takeaways from control barrier function is that the key insight is control barrier function predefines the safe set and tries to always stay in the safe set, assuming that all the assumptions are still being made. And implementing control barrier functions is minimally invasive, which means that it only modifies the nominal control if it's absolutely necessary. The good thing about control barrier function is that it is used to verify safety properties of a set without going through the difficult and computationally expensive task of computing the reachable sets, which Cherie talked about. So it's computationally more affordable. But the disadvantage of control barrier function is that it basically doesn't really work when our assumptions are violated. And it can get stuck in a deadlock situation when the system is completely symmetrical. Also, this is not exactly a disadvantage, but it makes control barrier function not a little bit case specific, which is for any application, we need to design our custom safe set, and it reduces the modularity of it, kind of. Any questions about control barrier function?
Hi, Mohammed. Can you show the previous slide? All right. So you say that the safety filter filters the control signal from output from controller. For example, for the image shown in this slide, the controller outputs a desired control signal, but the safety filter decides to change it to make it safe to execute.
Yes.
So from the point of view of controller, is that means that its command didn't execute exactly as the controller expected? Does the safety filter have any effect on controllers?
I can see what you mean. It doesn't have much effect on controller itself because controller has a real-time feedback and it's still trying to go towards the goal. So it keeps giving in collision control inputs, but safety filter will change it. But the problem that you are raising right now happens more on the planner side. So because planner is higher level, and it has lower fidelity of feedback. Planner plans to go somewhere, and if there's a lot of safety problems and there's a lot of change in between, planner gets confused because its plan is basically not being executed. The one solution for that is to give feedback from the safety filter to higher level planner whenever the control input is changed, and inform planner of this change that is being made.
Okay, thank you.
Any other questions? Okay, so back to Cherie.
All right, thanks, Mohammed. So just now we talked about the mathematical formulations that's needed to verify an action either being a trajectory or a control input that Mohammed talked about. And let's see kind of like how well these can, what are some challenges where this might fail, and we'll also talk about one key way that we can, people are beginning to address this. So kind of back to our key figure, where we're going from kind of like specialized cases into ubiquitous autonomy, where the real world, where we don't really know what are the potential cases that our system can face. So I guess at this point, are our current tools sufficient? So kind of looking, comparing the common model and real world, we're going back to our key ingredients of like dynamics, disturbance, these are just a few examples. We can actually see that our common extracted model and kind of the real world deviations. For example, in vehicle dynamics, we generally abstract it as like an integrated model, often at second order. So that means it's an acceleration-based model. However, in the real world, these can be highly nonlinear with a lot of dynamic constraints. Similarly, a key one is the external disturbance, such as wind, where the common abstracted model, such as the one we talked about in the reachability analysis, we use a bounded additive wind. However, in the real world, these may actually be state-based and may actually be out of the bounds that the expert has defined while doing the verification. And then last, a third one can be a state estimation error. Often this is actually missing from a lot of the safety analysis. And in the real world, this is a state estimation error is a key uncertainty that us in field robotics always have to deal with. So we'll kind of look at what can happen when the model is violated, specifically the external disturbance, and one way we can use to better address this. So again, going back to our previous verification mathematical formulation, we define a preset bounded disturbance, and generally we do this for one set. So first, we may have computed a reachable set based on, we'll just use wind as a unit based on 2 winds. And then the blue set is the reachable set that was pre-computed, and then that is verified safe as it's not in collision. However, suddenly we actually experience outside of bounded disturbance, so we have 2 more winds coming out from the left side. So this can cause the actual trajectory that the helicopter experiences as to leave the reachable set, to previously verified reachable set, and therefore it's actually unsafe. So here, the model, our assumption is violated when the disturbance is outside of the assumption. So one naive way can be, oh, why not just verify for a higher disturbance? However, this may cause a performance loss. For example, here we see one in our key example that perhaps the optimal trajectory is actually more in a straight curve. However, because we are doing we have pre-computed a reachability analysis with a higher disturbance, even though in reality there's a very small wind and can actually track it very well, we end up choosing a path that is lower performance. So again, this is going back to our key challenge of balancing safety and performance. So one option that people are starting to look at is adapting these kind of safety verification online based on the current estimation. And kind of one way that we have proposed doing this is pre-computing these reachable sets at multiple disturbances. So basically at like multiple disturbance models in a way. And then online, using the information, the disturbance information, to adapt our margins on the fly. So kind of going back to the running example, how this can be used. We also do this in a trajectory library framework. Here, again, with our running example, we have 3 trajectories that we can choose from. So it senses that it's at low wind and uses the smaller reachable sets. And all of these are actually in safe, verified safe. And we finally choose the straight line path, which is goes straight to the goal. And at high wind, the original trajectory that we chose in the low wind condition is in collision, and we choose one of the left or the right turn. So here we adapt in order to better balance safety and performance while giving safety guarantees. So in summary, we talked about why ensuring safety is important. Some of the key challenges being the underlying challenge being safety versus performance, which is exponentiated by the increasing complexity of our algorithms and the number of tail-end cases that we have in more and more applications that we're going into. We also talked about 2 key formal verification tools where we have reachability analysis that, as Mohammed says, estimates the possible states that a system can be at given a certain action. Whilst in the control barrier function, we predefine kind of what the dynamics should look like in order to give a guarantee on where the barriers of the system is. And we talked about how this may fail when the model is deviated and potential methods to alleviate this challenge. So we have some of the open questions and trends is how to know how well we have covered these cases for complex systems. As Mohammed talked about just now, these complex systems now may have like neural network, a lot of learning-based system where it's very unclear how we can actually span all to test for coverage. Second, how can we still stay safe even when our previous assumptions are violated? One potential way we talked about is basically by having multiple assumptions and then adapting which assumption to choose in order to get that verification. And lastly, a current trend, especially in the autonomous driving case where there's a lot of telling cases, is proving based on many simulated statistics. So another open question is how can we best design these simulators to properly stress test our complex algorithms? And what do these statistical proofs mean in real life? So that's all we have for the lecture session. Is there any questions that Mohammed and I can answer about our material? All right. Cool. So we'll go on to our interactive session that Mohammed will lead.
In the interactive session, we're gonna go through control barrier functions that we just introduced. You're gonna implement that safety filter, which lies between the controller and our system itself. So the way you do it is that you are provided with the nominal U, and you are trying to construct that optimization problem that comes up with the U star. So the first exercise is to constructing that optimization problem itself. So if you run exercises.py, you should see something like this, which is two robots going towards a goal point. And because the barrier function is not being implemented yet, they go through a crash. And the controller here is just a simple controller that always tries to go on a straight line towards the goal. So what you want to do is to fill out the compute safe control function in ecbfcontrol.py to implement the control barrier function optimization problem that we introduced today. A and B is actually already in the code, but you can use compute A and compute B functions to derive the constraint, and then you want to construct the optimization problem. And can we go to the next slide? Yeah, so a little bit more into detail, what you want to do to construct the optimization problem is you want to construct the optimization problem on the red box, but what you have is CVX opt QP solver basically. And CVX opt has this general form. So what you want to do is to change this red optimization problem to the general form to feed it to the QP solver. And this is how you can use it. And here you can see what P, Q, G, and H mean. And in terms of the difference between argmin and min is that this QP solver tries to minimize this objective given this constraint. And here you can get the argument that actually minimizes that objective. For example, if you get a solution Y, that gives you the minimized objective. So I think that's all you need, but if anyone has any problem going through it, let us know.
Hey, Mohammed.
Yep.
I think we are supposed to fill in codes in the function compute safe control in ecbf-control.py.
Yes.
Can I ask what's the type of the variable u underscore ds? Is that a non-py array?
Which variables again?
The u dash des returned from compute mon control function.
That's a numpy array.
Oh, maybe all of them are numpy arrays, like capital A, B. Okay.
All of them are numpy arrays, and the function itself needs numpy array from you.
Okay.
going through the math from our original optimization problem, opening it up, we'll get to this, which is in form of our QP solver. Here you can see the solution to the exercise 1. As we went through the math, P would be just the identity matrix. Q would be negative of U desired because the general form in itself had a half. And G and H were already in the general form. So G would be A, H would be B, and we go through the QP solver and get the argmin and pass it to optimized U. And if you run it, you should see this result. So you can see that because this situation was quasi-symmetric, it did go through a deadlock-like situation, but because it wasn't completely symmetric, because of the initial positions, we didn't go through the deadlock. So for the next exercise.
All right, while Mohammed comes back to Zoom, basically exercise 2 is on, we're gonna add multiple robots to this. So just now we had 2. If you can follow the instructions under exercise 2, under exercises.py, then under exercises.py, then we'll see a 4 robot and 2 obstacle situation. Awesome. So basically, we can kind of see how these, in the multi-robot situation, how this works. And then let's see. So here, we're actually going to recreate one of the classic scenarios that Mohammed talked about, which is deadlock. And in order to do this, you'll need to change the initial positions and goals of all 4 robots.
So basically here you need to create a completely symmetrical case where the deadlock happens. And after you get done with the deadlock, as some kind of a hacky solution, try to add some random value to our optimized U to get it out of the symmetrical situation to resolve the deadlock. So the animation on the left is the deadlock situation, and on the right is with resolved noise. So here's the solution for the deadlock situation, which is just changing the initial position and goals to be on the axis. And this is what you can see. So all the robots are in complete deadlock and will always be there. So one hacky solution that you can do is to add some small random value to our optimized U for it to avoid going into symmetrical situations. So whenever it's in symmetrical situation, all the robots have different random values added to their control. So the result of that would be something like this. Oh, sorry, I didn't save it. So that concludes our interactive session.